Good afternoon, friends. This is Dr. Kushal Bhattacharya, and today I should discuss on the force analysis of rolling contact bearing. Now, for this, we have to concentrate on the figure. How does the figure looks like? First, we see what are the forces acting on it. First, we see if a shaft is there and the bearing on, if the shaft is lying on the bearing, what are the forces acting on the shaft. So first, we get a radial load which is acting on the bearings. So this radial load is represented by this. So this is the radial load, and all the bearings share the load, share the load which is acting on the center of the shaft. It has been shared by all the bearings. So you could see here the balls are lie on this part, and the radial load of the bearing is shaft on the shaft is shared by all the balls, all the balls lying on the bearing. Now the second one is the axial thrust. Now this is the thrust coming on the bearing from this side. If you see the side, if you see this picture, this is the thrust coming from this side. So it is represented by this. So this is the axial thrust. Basically, an upper half of the bearing housing is there, and over which lies the balls, and from there it is getting a force. It is getting a force on the axial direction. It is getting a force on the axial direction, which is you see in the axial bearings. Now you could see another type of load, which is called as a moment load. The moment load is created like this. Suppose if a load is applied from here, and if the direction of the CG of the load is applied, or the CG of the shaft of anything if is there, so the distance from here to bearing, it will cause a moment, it will cause a turning moment. So this moment is represented by this diagram. So here all the balls are lying, and it will cause a moment to it, Now basically we should come to the discussion of what is equivalent load. Now you could see there are two types of loads. If you did not consider the moment load for the time being, so if you for a specific bearing, so if you consider what are the loads acting on the bearing, you could see one load is the radial load, and another one, the load is coming, is the thrust load. So the first one you could see the radial load is acting on the bearing, and the second one is having a thrust load on the bearing. Now we should go for a hypothetical load. Then what is the definition of this hypothetical load? So now you convert these two components into an hypothetical load. So now the hypothetical load can be compared with the dynamic load capacity. Now what is dynamic load capacity? I should just follow my after this discussion. Now the equivalent dynamic load is defined as the constant radial load in the radial bearing. If the bearing is radial, so it is a constant load in the radial bearing. So if this is a radial bearing, so this is a constant load in the radial bearing. So or thrust in the thrust bearing, or thrust, if you see the thrust, or the thrust in the thrust bearing, which if applied to the bearings could give the same life as that which the bearing will attain under actual condition of force. That means in actually what are the forces applied if they are maintaining that conditions, the boundary conditions, if the hypothetical load give the same life, then the expressions could be written at P is equals to XFR plus YFA, where P is the equivalent dynamic load, in Newton, and X and Y are and FA and FR is the radial load. This is the radial load, and FR is the radial load, and FR, this is the radial load, this is the radial load, FR, this is the radial load. And what happened, FA is the axial or thrust load, and FA is the axial or the thrust load. So and therefore X and Y are the radial and thrust factors respectively, and their values are given in the manufacturer's catalog. Now the dynamic load carrying capacity of a bearing. Now how does the dynamic load carrying capacity of a bearing is designed? Now the thing is that first what type of failure? Normally bearing is accustomed with fatigue failure. Now as because the bearings are subjected to a fatigue loading, because it is subjected to a shaft, and as the shaft moves the ball bearings are subjected to a fatigue loading. So fatigue, as because it is subjected to a fatigue loading, so the life of a bearing is calculated in terms of the fatigue life. Now how does the fatigue life is defined? Fatigue life is defined as the number of cycles or number of hours the bearing sustained under the applied load before the development of the first fatigue crack. Now if you see that if you see that if a bearing what happens, if a bearing is there, now what happens when a bearing this is the inner race of the bearing, and this is the outer race of the bearing. Now as what happens basically when the shaft moves, so what happens, it is the analysis of a beam, as I've discussed, is limited to fatigue life. So what happened, it is as because it is mainly considered of fatigue failure or fatigue loading. So what happens, so the life of the bearing is mainly considered with fatigue life. Now what is fatigue life? Fatigue life is the number of cycles or number of hours before a crack generates. So before if a number of cycles the balls has moved, or the number of cycles the load is applied before the first cracks generate, let the number of cycles be n. After that what happens, the fatigue crack develops either on the bearing ball or on the race. So then it could be caused as the bearing failure. Now how to calculate the bearing life, or now prediction of a bearing life is a very difficult. For example, if we consider there are 10 number of bearings. Now for example, take it, there are 10 number of bearings. Now there, if we consider now for a radial bearing, there are 10 number of bearings. Now for what, how to consider the failure of the bearings. Now there are basically prediction of the failure of the bearing is a very difficult task to perform. Now there are two ways to solve it. First way is that we draw a curve. We basically draw our curve on the x-axis. We represent the number of bearings, and on the y-axis we predict the RPM, the number of RPM. Now what we could see that basically if there are 10 bearings, we take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now what happens, we calculate for each bearing, if we calculate the number of what is the number of RPM n for bearing 1. So before the advent of the first crack, so we put this number n1 over here. We put this value of n1 over here. So it could vary like this, or it could be distributed like this, it could vary like this. So now what happens, now there is two ways of measuring this. The first way, this is the x-axis, the number of bearings, and y-axis the n, the number of, that is the number of turns before the first fatigue failure occurs. Suppose for one bearing it has achieved up to this limit. This is n1. For 2, let it be n2. For 3, let it be n3. So like this. So what happens, how to calculate, if there are 10 bearings, how to calculate the fatigue life of the bearings? Now one approach, the first approach is a very common, the statistical approach to solve is that, the first statistical approach is solved to that. The first one, the statistical approach, we could see that we could take the average values, that is n1 plus n2 plus dot 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 up to n. That is, each bearing have achieved this number of cycles before the first failure occurs in them, divided by the total number of bearings. That is one approach. Another approach is that, which is the second approach, which is most widely accepted, is that it is taken as the that is 90% of the bearing, that is the load on which the load on which the 90% of the bearing has achieved a fixed value of n, So we take an assumed value of n and we say that 90%, if we call it the 90% of the bearing, if we say that the 90% of the bearing has achieved, 90% of the bearing, suppose 90% of the bearing has achieved, as 90% of the bearing has achieved that length, achieved that number of cycles. So if you consider the 90% of the bearings achieve that, so upon if you take 10 bearings, so we could say that 9 bearings has achieved this value of n before the first failure occurs. So if we take 90% of the bearings, that is 9 bearings. So if there are 10 bearings, there is 9 bearings has achieved this value of n. You could see that 90% of the bearings has achieved. Suppose this value of n is taken like this. This value of n is taken like this. This n, the value of n can be 1 million revolutions, no problem. So that 90% of the bearings, that is, if there are 10 bearings, that is 9 bearings has achieved this, only 1 bearing cannot achieve. For if you take 20, so there should be 18 bearings, 18 number of bearings which has achieved the value of n before the first fatigue failure occurs. If that is 30, what happens? If there is 30, then the 10% of 30, it should. Now if there are 30 is there, so what happened? Then 19 to 30 bearings are there, then 27 bearings have achieved this value of n. If 20 bearings are there, 18 bearings have achieved the value of n, and if 9 bearings have achieved the value of n. So we go a factor of 90%. So that is called the rated life, that is the 90. So we could see that if there are 10 bearings, the 9 bearings have achieved a life of 90%, that is 9 bearings have achieved the value of n before the fatigue failure occurs, 2018 and 3027. In this way it goes. So we could see that what happens basically is that if the number of bearings, if you could see that if the number of that is 90% of the bearings, 90% of the bearings have achieved the value of n, which is a predetermined value. Can it be 1 million cycles or whatever? So before the fatigue failure occurs. Now you can take for example, but the life of a separate bearing, suppose we take the bearing number 1, the life of separate bearing n1, life of n2 can be different from the rated life. But it is seen from statistics that even 50%, if you go for the 50% of the bearing, if you go for the 50, that is, if it is 10 bearings are there, 5 bearings, that is 50%, 1, 2, 3, 4, 5, among the 10, 50% of the bearings, they did not cross the rated value of n. Not only cross the rated value of n, but they have gone 5 times more than the rated value of n. They have gone 5 times more than the rated value of n. This could be shown. Now we could see that the 50% of the bearings, out of 10 has crossed not only this value but 5 times the rated value. This could be proved. This could similarly for if there are 20 bearings are there, 10 bearings not only cross this value of n, but they have crossed 5 times the value of n. Similarly for 30 bearings. So this is the reason why the taking 90% is a safer side. Now the thing is that now we come, what is dynamic load carrying capacity? So now we come to dynamic load carrying capacity of a bearing. Now dynamic load carrying capacity of a bearing can be considered as that load. Dynamic load carrying capacity of a bearing can be considered as that load under which 90% of the bearing has achieved, 90% of the bearings has, symmetrical bearings have achieved a life of 1 million revolution. 1 million revolution. That 90%, that means what? Dynamic load carrying capacity of the bearing can be defined as the radial load for radial bearing and axial load for axial bearing, so that it has covered 1 million revolution before the development of the first fatigue crack, So what is 1 million revolution? 1 million revolution is that revolution which is taken as a datum line, so that 90% of the bearings has crossed this life. Now if we go to calculate the load life relationship, now we design a relationship based on the bearing life, the dynamic load carrying capacity, and the equivalent dynamic load. Now these three parameters are interrelated by this equation, which is given by L is equals to C by 5 to the C by P to the power 5. L is equals to C by P to the power 5, where L is given as the bearing life in million revolution, C is a dynamic load carrying capacity N, and P is the equivalent dynamic load. Based on this, we get the value of L. Now P is normally taken 3 for ball bearing and 10 by 3 for roller bearing. Now L can be calculated in working hours. So this is how L is equals to 60N by LH by 10 to the power 6, where LH is in life in working hours. So L is equal to 60N by LH by 10 to the power 6 gives LH is equals to life of the bearing in working hours, and N is the number of RPM. N is the number of RPM, the number of times the shaft is moving, the load is applied, the number of turns the load is applied, or the number of cycles the load is applied. Now for selection, now another important term which come across for load factor. Now basically, what is load factor? Now whatever load we have calculated for a bearing, for a bearing conditioning, taking into consideration of the equilibrium condition. If you recall the static load condition, we have taken the Stevak equation and we have calculated it based on the static load condition. So now the bearing can be driven by a gear or any other sort of machines, by pulley. So for that reason, what happened, you have to multiply with a load factor. So the static load factor, when multiplied by that load static load bearing capacity, when multiplied by this load factor, we can get the dynamic load carrying capacity of the bearing. That means static load bearing capacity, when multiplied with the load factor for different conditions, we can get the dynamic load carrying capacity of the bearing. Now we go for the selection of the bearing. Now how selection of the bearing is there? First, if a selection of bearing is required, we should calculate in the equilibrium condition the radial load and the axial load. We could first, my job is to calculate the radial load and the axial load. Then we should find out the bearing based on its application. We should choose the bearing based on its application. Then we have to find out this value of the value of x and y. So we have to find out the value of x and y for the equivalent. We have to calculate the value of x and y for the equivalent dynamic load. Now x and y can be available from the catalog if we know the value of f by r or f by co. Either you have to know the value of f axial load by radial load or axial load by the static load. So this is provided on a table. I am showing the table. In the following table, the values depend upon the two ratio Fa and by Fr and Fa by Co, where Co is the static load carrying capacity. The selection of the bearing is therefore done by trial and error. The static and dynamic load capacities of single row deep groove ball bearings of different series are given in another table. Now to begin with, a bearing of light series such as 60 is selected for the given diameter of the shaft, and the values of C0 is found from that another table. Knowing the ratio of Fa and C0 and Fa by Fr, the values of x and y are found out from this table. Value of P is equals to, that is the equivalent dynamic load. P is equals to x Fr plus y Fa, where there is no provision, that we have to multiply with the help of the load factor to get the value of the dynamic load. Now, when this value up to 4 we have achieved, then we have to make decision of the expected pairing life. Now, expected pairing life can be find out from this equation, from this table, basically, from where the table shows that for automobile cars, the life in the expected life is 50 million revolutions. For trucks, it is 100 million revolutions. For trolley cars, it is 500 million revolutions. For railway road cars, it is 1000 million revolutions.